Yo estoy presentando, no se nota.
Okay. Engineer, good evening. Today we will talk about the topic prediction of the scope and type of natural disaster caused by rain in Peru. Uh, my group is conformed by Berenguel Olivares, Mauricio Javier, Briceño Vera, Jesús Alberto, Tongo Cruz, Frank Yamir, Flores Portugal, Roberto Ramsés, Salazar Valencia, Anderson Javier, and Valencia Flores, Christian Henry. And we have started this exhibition.
Henry.
The report presents a study of the prediction of natural disasters caused by heavy rains in Peru, highlighting the caused use of convolutional neural networks to provide prediction accuracy. The analysis focuses on the methodology, covering data collection from methodical, logical, geospatial source of development of CNN models and their integration into early warning systems. The importance of theoretical framework is imprecise, showcasing the application of CNN in satellite images analysis of the and the detection of weather predators. The main objective is mitigate of the devastating effects of serious events of vulnerable communities in the country.
Introduction. Peru's diverse geography makes it susceptible to natural disasters like floods, landslides, mudslides, and avalanche during the rainy season, which severely impact communities, infrastructure, and the economy. Predicting these events is essential for effective disaster risk management involving the collection and analysis of meteorological, geological, and hydrological data using convolutional neural networks, specialists in processing visual data, and can enhance the prediction of these disasters by analyzing satellite images and other meteorological data. This helps in using early warnings and implementing preventive measures to protect vulnerable communities.
Objectives. Developed a predictive model based on convolutional neural networks, CNN, to anticipate the extent and type of natural disaster caused by intensive rains in Peru. The goal is to improve predictions accuracy to facilitate evacuation and the implementation of preventive measures that protect communities and their asset. Specific objectives. Identification and analysis of relevant data, select and analysis meteorological, geospatial, and hydrological data. Source necessary for accurate prediction of natural disaster caused by rain. Data source include high resolution satellite image, historical rainfall records, temperature, humidity, and topographic characteristics. Develop an efficient system for data collecting and storage, ensure data integrity, accuracy, and accessibility for CNN model training, development and training of the CNN model, design of convolutional neural network, architecture adapted to the analysis of spatial and temporal data, configure convolutional pooling and fully connected layers to capture relevant features of natural disasters. Train to CNN model using collecting data, advanced aplica avances processing techniques such as normalization, data augmentation, and noise reduction to improve input data quality. Implement regularization and optimization methods, enhance the model generalization, capability, and avoid overfitting. Ensure accuracy prediction in various methodological scenarios. Model validation and evaluation, conducting thorough validation, evaluate to CNN model, accuracy recall, specific and F1 score to ensure its effectiveness in prediction for different types of natural disasters caused by rain. Compare the CNN model performance with traditional predictive methods, demonstrate the model superiority in the terms of accuracy and early detection capability and not adversing meteorological events. Integration into early warning system and training develops interface and tools integrate the CNN model into existing early warning system, facilitating the generation of accuracy and timely alerts for authorities and communities, design training programs for vulnerability communities, focus interpreting alerts generated with CNN model and adopting appropriate uh, preventive measures such evacuation and asset protection, threat educational materials and organization workshops and drills to strengthen community participation for natural disasters. Yeah.
Materials and methods. A collect and pre-process high-resolution meteorological, hydrological, and geospatial data, satellite and images result. Obtain high-resolution data from satellites and such as Landsat, Sentinel, and others. Provide visual information of terrain and weather bodies. Meteorological data. Collect historical and real-time data on precipitation, temperature, humidity, atmospheric pressure, wind speed, and direction. And solar radiation. Sources such as water stations, sensor networks, and meteorological engines like tsunami are fundamental. Hydrological data obtain information on rivers levels and flows, as well as soil moisture content. This data can come from ground sensors and hydrological models. Geospatial data include information on geographical coordinates, latitude and longitude, altitude, terrain slope and land cover, forests, urban areas, water bodies, etc. Data pre-processing normalization adjusts the data to a common scale to facilitate model training. Data augmentation generate variations of images to increase the amount of training data and improve model robustness. Data cleaning remove or correct erroneous or missing data to ensure data set quality. Design and train CNN models using historical and real-time data. Model architecture. Design a convolutional neural networks architecture suitable for task and consideration factors such as number of layers, feature size, and activation foundation. Training dataset. Use historical data to train the model, ensuring a variety of weather patterns and disaster scenarios. Optimization technique. Use optimization algorithms such as stochastic gradient descent, ADAM, or RMS probe to minimize the loss function and improve model performance. Regularization technique. Apply method on such turbo 1.L2 regularization and batch normalization to prevent overfitting and enhanced generalization. Evaluate the more recurity and performance using cross-validation technique and performance metrics. Cross-validation use full cross-validation to evaluate the model's performance on different success of the data set. Performance metrics use metrics such as accuracy, precision, recall, F1 score, and ROC, IUC to assess the model effectiveness. Implement the model in early warning system and test under real conditions. Adjusting the system as necessary. System integration. Integration the training CNN model into early warning system to process real-time data and generate alerts. Real-time testing. Test the system under real conditions to evaluate its accuracy and reliability. In prediction natural disaster. System adjustment. Adjust the model parameter and system components based on feedback and performance evaluation. Theoretical framework. Convalidation neural networks (CNN) and their application in satellite images analysis. Convolutional neural networks, a type of deep learning model to excels in image processing by capturing spatial hierarchies, top convalidation layers. CNNs include convalidation polling and fully connect layers for future extraction and pattern recognition. Satellite images analysis. Satellite images provide insight in the air surface, surface water patterns, terrain features, and vegetation covers. CNN can analyze these images to detect complex patterns and changes, aiding in identification flood or landslide-prone areas by elevation, land cover, and precipitation. Prediction of natural disasters. CNN training on historical data can predict natural disasters like floods and landslides by analyzing satellites, images, and meteorological data. This enables early warning and preventive measures. Application in Peruvian context. Peruvian geography and weather patterns present challenges for disaster prediction, by incorporating regional data like precipitation, river flows, and topography features. CNN models can accurately predict natural disasters, helping to mitigate their impact on vulnerable communities.
So we have the methodological approach. At the first point, we have collect and preprocess high resolution meteorological, hydrological, and geophysical data. The collection of high resolution meteorological and data is crucial for training effective convolutional neural network, or CAN. Model is predicting natural disasters caused by heavy rains. This process involves obtaining data from various sources, such as satellite images, weather stations, and ground sensors. We have the satellite image data, obtain high-resolution images from satellites like Landsat, Sentinel, and MODIS. These images provide visual information about terrain, water bodies, and vegetation cover. Also, we have meteorological data that collect historical and real-time data of precipitation, temperature, humidity, atmospheric pressure, wind speed, and direction. Also, the solar radiation. Sources like weather stations, sensor networks, and meteorological agencies. In the case in hydrological data, we have the formation of river levels, flows, and soil moisture content. This data come from ground sensors, hydrological models, and monitoring networks. And the geospatial spatial data include the geographic coordinations, altitude, terrain slope, and land cover. In the case in data processing, we have the normalization that adjusts data to a common scale to facilitate model training. The data argumentation generate variations of images to increase the amount training data. And the second point, we have the design and train CNN models using historical and real-time data. The design and training of CNN models for natural disaster prediction involve selecting an appropriate architecture and using historical and real-time data to train the models. We have the model architecture, design and CNN architecture suitable for the task. Consider factors like the number of layers, filter sizes, and activation functions. The training data use historical data to train the model, ensuring a variety of weather patterns and disaster scenarios. The optimization techniques use an algorithms like stochastic gradient descent, ADAM, or RMS probe to minimize the loss function and improve model performance. In regularization techniques, we have to apply the methods like dropout, 1.2 regularization, and batch normalization to prevent overfitting and enhance generalizations. At the third point, we have the evaluate the model's accuracy and performance using cross-validation techniques and performance metrics. Basically, it's evaluating the model's effectiveness involves using cross-validation techniques and performance metrics to ensure accurate and reliable predictions. We have the cross-validation, use k-fold cross-validation to evaluate the model's performance of different subsets of the dataset. And performance metrics use metrics like accuracy, precision, recall, F1 score, and ROG AUGDO to assess the model's effectiveness. And the last point, we have the implement the model to in early warning systems and test user real conditions, adjusting the systems as necessary. Basically, implementing the model in an early warning system involves integration the training CNN model to process real-time data and generate alerts. We have the system integration, integrate the CNN model into early warning system that can process real-time data and generate alerts. Also, we have the real-time testing, test the system under real conditions to evaluate in accuracy and reliability and predicting natural disaster. So we and the system adjustment, use the model parameter and system components based on feedback and performance evaluations.
Okay, now I talk about results and discussion. First, have the data collection and preprocessing. Meteorical data includes precipitation,
No se te escucha.
sorry. Now I have the results and discussion. Okay, I first talk about data collection and preprocessing. Meteorical data includes precipitation, temperature, humidity, atmospheric pressure, wind speed and direction, and solar radiation sources from weather stations, sensor network, and meteorological agencies like tsunami. Hydrologic data encompasses rivers level flows and soil moisture content from ground sensors, hydrological models, and monitoring networks. Geospatial data contains geographic coordinates, altitude, terrain, slope, and land cover. Third, we have the model training and evaluation. The training data uses 10 and 20 years of historical data to capture various weather patterns and disasters scenarios from model training. Cross-validation employs scaffolds cross-validation to assess model performance by dividing data into K parts, training on K1 parts, and validating on the remaining part repeat K times. And now performance metrics are assessed using accuracy, precision call, F1 score, and rogue out to evaluate, predict capabilities and event identification accuracy, and now implementation and testing. Systems integration integrates the training CNN model into an early warning systems that processes real-time data and generates alerts in real-time testing, tests the systems under real conditions, showing accurate predictions of natural disasters caused by heavy rains, allowing early warnings and preventive measures. System adjustment fine-tunes model parameters and system components based on feedback and performance evaluation for accurate and useful alerts. And finally, the conclusion. Okay, the implementation of convolutional networks, neural networks, or CNN for predicting natural disasters caused by heavy rains in Peru has shown significant potential in enhancing prediction accuracy and reliability by collecting and pre-processing high-resolution meteorological, hydrological, and geospatial data, designing and training CNN models, and integrating these models into early warning systems. Authorities can make informed decisions to protect vulnerable communities. The results demonstrate that CNN models can effectively identify patterns and relationships that precede natural disasters, providing early warnings and enabling preventive measures to mitigate their impact. Future work will focus on further improving the model's performance and expanding this application to other regions and types of natural disasters in Peru and Arequipa. And that's all in engineering, Javier, and this is the presentation.